Recording is on.
That must have been Eric.
So I'm not the only one that's seen videos locking up.
Yeah.
Wow.
You and I are the only ones moving.
I don't know. Like right now, Kevin, Michael, and Ian are frozen. So is Frank.
Well, I'm seeing Kevin. I'm seeing Peter, Kevin. No, Kevin's not here. Yes, he is. I'm seeing him. I'm seeing Ken. I'm seeing Peter. I'm seeing Ian. Eric, I think, is moving. And Frank is moving. Everybody's moving now.
Isn't that weird? Like as soon as you started to speak, I could see you move, Michael. But Kevin, for me, is still frozen. I don't know. Anyway.
Okay.
As long as the presenter isn't frozen, then that's good.
Yeah, a lot of people are frozen. Holy cow.
Well, the other thing is we could just leave video off unless you're speaking. If that makes it easier. I don't know.
See what happened again. As soon as you started to speak, Kevin, you unfroze.
Oh, really?
Yeah.
Well, when Kevin spoke, the little blue bar around the little blue rectangle around his picture came on, and he's moving. He was before, so I don't know.
Oh, so if I start talking again, oh yeah, okay, it picks up on me and it moves the blue, border, whatever.
Yeah.
Also, it switches off the video if you don't have the border.
Maybe that's it.
Yeah, I can see that now. Everybody's frozen, and then as soon as you speak, you unfreeze.
Yeah, weird.
Is this a new version of Jitsi?
Yeah, maybe they're trying something out to reduce bandwidth.
Possibly.
Not from my side. Everybody's moving. Everybody's talking. Looks normal.
Hi, Dave.
Oh, well.
Yeah, I'm looking for something in the settings, but I don't see anything.
Yeah.
So who's in here now? Jerry, Eric. Who's the fellow Jitster? Ah, the Mr. Paris himself. Okay, I guess we should get going here. Good evening, everybody. So I don't think we have anything here. Anybody new? It's Hassan, Dave, Jerry, Eric. Yeah, nobody new. Okay, we're good to go. So tonight, we're going to have Michael talk about the RF amplifier design process and LT Spice. Dave's going to kick off the show us your half-built shack, and Kevin's going to give something on cool chips, and then the rest is open. So without further ado, you want to go ahead, Michael? Everybody's locked up. Michael, can you hear me?
Yes. Yeah, sure, I can hear you. No problem. Yeah.
Oh, okay. No, you were locking up.
Oh, okay. I don't know why. I was just trying to share my screen. So, okay. So now let's see. Share your screen. Application window. There it is. So hopefully you guys can see a presentation, right?
Yep.
Okay. I guess I'm going to go to slideshow here. Let's start from the beginning. Okay, right? Everybody can see it?
Yep.
Okay. So this is actually a build on from Peter's presentation last time on the common emitter amplifier experiment, and that came from Ward Silver N0AX's hands-on radio series, and there was one on the common emitter amplifier, which is what Peter based his on. So I was going to talk a bit more about where the component values come from when you're doing a design. And the key things seems to be there's really no hard and fast rules about this. It just, there's a lot of assumptions go into this, and some of them make a difference and some of them don't, I guess. And the way it used to be done, you used to start with a transistor characteristic curve and play around with that. But people like Charlie Morris, ZL2CTM, point out that you can't really get those characteristic curves very easily. I was able to find one for the 2N3904, which is what this thing is based on. But anyway, there's basically what you do if you don't have the curve, you sort of make some assumptions. And you just sort of use some basic assumptions about what you want to do, and you use rules of thumb as well. So this is Peter's common emitter amplifier, the LC spice drawing, and you can see there's resistors and capacitors, and they've all got values and stuff. So what I'm going to talk about is how you get there. So one way to start is to talk about the basic transistor model. And on the left here, transistor basically is a set of semiconductor material that's been doped with, in case of the N, it's been doped with more electrons than holes. So, and the P is got holes rather than electrons in it more, and the other end, and they're joined together. And the characteristic of a transistor is that while this part here between the P and the N is actually a diode, and it's forward biased, as you can see, because you've got positive voltage on the middle and negative voltage on the bottom. The other one, from the PN at the top, is reverse biased, basically because VCC is higher than the base voltage VBB. So anyway, when you set it up this way, it's a current controlled device, and by injecting base current into the transistor center point, the base junction, base point, you get current flowing from the collector to the emitter. And because the base current is very small, it amplifies the base current. So the middle diagram is, of course, the standard transistor diagram for an NPN. And on the right-hand side, these are the small signal models. There's a whole bunch of them. But basically, you can think of this as a diode between the base and the emitter on the left here, with some resistance in series. And you can show that resistor can be put in the emitter circuit here as a small resistor, little RE it's called. And the base current is related to the collector current is related to the base current by this beta, this ratio beta, which is a multiplying factor. And you can also further model it as a slightly different way to model it, with a base voltage here and a current source. This is a current source, of course, a current source with the GM, the conductance times the base voltage. Either way, you've got this little RE in the circuit. So that's sort of what it looks like. And the small signal model would be the AC model, of course. And anyway, so this is a typical output characteristic curve. It's got collector current on the left and collector emitter voltage on the right, on the bottom axis. And these horizontal lines here are differing values of base current IB. This is microamps here. This is milliamps over here. So what you can do with these things is these curves, is you can draw a line on here, the DC operating line, and over here it's your chosen collector current, for the sake of argument, 10 milliamps. And down on the right here, it's 13.8 volts roughly. So you can draw a graph like that, and you can show that if you calculate figure out what your collector current is, you can pick an operating point, say here where the arrow is, and you can calculate various things with this. And you can, ideally what you do is you pick your curve in the middle here, so your point in the middle, operating point in the middle, so that the transistor's got lots of room to swing, the voltages swing around. And these are straight lines here. This is pretty, the thing is you don't get much of an increase in collector current as the collector to emitter voltage increases. You can see that on the graph. These are flat. So anyway, that's what the characteristic curve looks like, and you can do a whole bunch of stuff with that. But I don't know how to do it. It's in the ARL handbook, and I suppose we could do it, but what you do is do other things. This is the generic. This is sort of a generic model. It's of course pretty well exactly the same as Peter's. There's the transistor. The DC biasing is done with these two resistors connected between collector, between the DC supply and ground, and there's an emitter resistor in the emitter circuit here. And I should mention, by the way, the emitter current is virtually exactly the same as the collector current because the base current is so small. Anyway, so you use the resistors to set up your bias. And this resistor up here is, I understand to be, one reason for it is to isolate the power supply from the transistor circuit itself. Helps to do that. These capacitors here, one is much larger than the other, but what they do is they make sure the AC, they make sure this point here is AC ground, and they also keep noise out from any noise from the where's my mouse gone? They also keep any noise from the power supply out of the circuit because they ground it. So yeah, this is if I were talking about a feedback amplifier, I would have this point connected to the base, and that provides negative feedback to control the gain and flatten out the curves and the gain versus frequency curves. Matching transformer here on the output, another one here on the input. The point of this is to make sure that you match on the input. For example, you match your where's my mouse gone? Where'd it go? Where did it go? It's gone. Oh, there it is. It matches the input impedance of the voltage source, or whatever the previous stage happens to be, to the transistor, the amplifier input resistance. And likewise on the other side, on the output, transformer does the same thing. It matches, in this case, 50 ohms because I put a 50 ohm load there, so it matches that 50 ohms to the impedance of the circuit on the left-hand side, which is, and ideally, I think the way to look at this is you want for maximum power transfer, you want to set things up so that the impedance presented by the load side here is the same as the internal transistor collector impedance, because that way you get the maximum power through the circuit because it's matched. And you should pick the turns ratios, as I'll come to later, to make sure that things are matched. Otherwise, you got a couple of coupling capacitors, and you've got an emitter here and over here, and you've got an emitter bypass resistor capacitor here, which basically puts the emitter at AC ground, but not DC ground. So, yeah. So there's some assumptions you have to make. This is where it gets sort of hairy. You're sort of making assumptions about things. You know that the collector current is equal to the HFE or beta DC times the base current. So you got to find a value of beta, and it's the DC value, and you can get this off the data sheets, transistor data sheets. Only trouble is, there's a whole bunch of different values. It depends on you get different values depending on whether you pick a 1 milliamp collector current or a 10 milliamp or 5 or whatever, and they give you a maximum and minimum. So you got a problem. How do you pick that? And also, from one transistor to another, the HFE changes, the beta changes. So anyway, you got to pick something. So you can pick halfway between the minimum and maximum, which is really rather arbitrary. You can take the geometric mean of the minimum and the maximum, or you can use the AC beta, which doesn't seem right because that's to do with those small signal stuff, but that would be the transition frequency, which is stated on the data sheet, divided by the operating frequency using gives you an AC value for beta. So one way or another, you come up with a beta value. Then you pick your collector current. And one thing to think about with the collector current is the higher the collector current, the smaller the internal resistance of the transformer is, the transistor is. So that's something to bear in mind when you're picking collector current. Likewise, the higher the collector current, the more current drain you're going to have on your battery. So that's that. And the other thing you have to do is pick the DC emitter voltage, and you want to keep away on the characteristic curve on the bottom. If you keep away from the left-hand side of the curve, that's the linear. Want to stay in the linear part of the curve where things are flat, where the collector current is pretty well doesn't change with voltage. So what you do is one way to go is to pick the emitter current to be half of the supply voltage. And once you've done that, you can then, having got the emitter current, you can calculate the value of the emitter resistance, the series emitter resistance you want. Just divide that voltage by the collector current, the emitter current ICQ, and that gives it to you. So now you got your emitter resistor value, and now you want to go on and calculate the bias resistor values. So what you do is you know that on a transistor the base voltage is 7.7 volts higher than the emitter voltage, so you use that to get your base voltage. And then you're in a position to do some more calculations. And basically what you do is you assume that the current flowing in the resistor chain from the supply down to the ground, that is where the base is connected to, you assume the base current is 10 times, the current flowing in those resistors is 10 times the base current, at least. So having done that, you calculate your resistor values, and then of course they're not standard values, so then you pick some standard values, and close enough is good enough. Yeah, so here's the way you go. And in 2N3904, the minimum value of the beta is 100, the maximum is 300, so you just arbitrarily pick 200. Then you choose your collector current, 10 milliamps. Could be 10, could be 1, could be 5. Then you go and calculate your emitter voltage. Like I said, the supply voltage was a 13.8 in this case divided by 10, 1.38 volts. Then you calculate the emitter resistor in series between the emitter and ground, which is that voltage divided by the emitter current, comes out at 138 amps. Then you go and you calculate what the base current should be. And I say should be because it isn't. It doesn't work out that way when you actually do it. But anyway, it's the collector current, the quiescent collector current, steady state collector current divided by the beta. So that comes out to 50 microamps. In the case of the LT Spice model that I built for this, it's actually about 35 microamps would appear. So anyway, you get that. And then you go on to calculate the values of the resistors, and the one at the bottom, R1, I think that's the right way it's around. It's basically that base voltage which you've calculated, which is around 2 volts normally, divided by 10 times the base current, which gives you 4.16K, and then you go through a calculation to get the other resistor value, which comes out at 19.49. So those aren't standard values, so you just pick them. So you pick the emitter resistor to be 130, R1, one of them to be 3.9K and the other to be 22K, sort of close. So then in the emitter circuit, there's a capacitor, bypass capacitor, in parallel with the resistor. So you basically, this is where one of these rules of thumbs come in. You basically choose the reactance of that bypass capacitor to be 1/10 of the emitter resistor value. So basically you go through the process of calculating the value of the capacitor from the formula that the reactance is 1/2 pi times the operating frequency times the capacitance. So that gives you a value for the capacitance, given that you've got an operating frequency. And a lot of these, if you're doing an HF amplifier design, then what you do for the purposes of this is you pick the operating frequency, the bottom end of the 80 meter band, because you know that that's going to give you the minimum reactance. So you pick that. And when you do that, in this case, you get 13.8 ohms for the reactance because it's 1/10 of the resistor value. So that means the capacitance should be 3.29 nanofarads. So basically you choose a 100 nanofarad capacitor because you know that the reactance is going to be way less than 13.8 and it's actually 0.45. That's fine, that works. And at the higher frequencies, it still works as well, so that's fine. Very arbitrary stuff. Then you're looking at the other next thing you want to do is calculate the input coupling capacitor value, and what seems to be done is another rule of thumb. It's less than 100 ohms, or it's less than 1/10 of the amplifier input resistance. And the amplifier resistance, input resistance, is the resistance of the two bias resistors in parallel, plus the little RE resistance reflected onto the base side. And that, to do that, you take that RE value, multiply it times the beta value +1. And in this case, because you're talking about small signal AC stuff, you use the AC value for the beta, which you calculate by basically taking the gain bandwidth product, which is that transition frequency, divided by the operating frequency. And in this case, 300 divided by, and you get the gain bandwidth product off the data sheet. Again, it's 300 in this case, divided by the frequency you're choosing, 3.5, you get 85.7. And the little RE value is related to the quiescent collector current. You take, it's 26 divided by ICQ, which gives you 26 divided by 10, or 2.6 ohms. So you stick all that in your formula to calculate the parallel combination of all this stuff, and you get 211 ohms. So that tells you, given the capacitor reactance is 1/10 of that, that tells you that the reactance has got to be around 21 ohms or less. So again, you just pick a 100 nanofarad capacitor, you get a value that's way smaller than that, 0.45 again. So that takes care of the coupling capacitor. And then the next thing, the next thing to deal with is the matching transformers on the input and the output side. And these are there to, on the input side, is to match the 50 ohm presumed source of the resistance of the source. If it's your signal generator, it would be 50. If it's the previous stage in the circuit, that would have been designed to be 50 as well. And likewise, the output is also 50 ohms on your transistor. So then you go to calculate the turns ratio of the transformer. And for a transformer, the ratio of the primary voltage to the secondary voltage is equal to the ratio of the number of turns on the primary side divided by the number of turns on the secondary side. And you can go through the manipulation and you can show that that means that the impedance on the primary side divided by the impedance on the secondary side is equal to the turns ratio squared. So then you can go and calculate your turns ratio, because you know on the input side, you know that input impedance for the circuit divided by 10 was 211 ohms. Divided by 50, that gets you the turns ratio of 2. And this is on and that NP is the number of turns on the transistor side of the circuit, the coupling capacitor side, not the other side. So you use a 2-to-1, a 12-turn to 6-turn transformer to get the 2-to-1 ratio, and you do it on a 3743 core, toroid core. There's another rule of thumb here. You check to make sure that the winding with the lowest numbers of turns, in this case the 6-turn winding, on the input side of the circuit has a reactance that's at least 5 times the load on that side. So it's got a reactance has got to be at least 5 times 50 or 250. So what you do is you take the 6 turns and you look up the calculator for a 3743, or you can calculate it directly. It tells you the inductance is 12.6 microhenries, so the reactance is 277 ohms at 3.5 megahertz. So it's 5 times. So you're good to 5.5 times. So you're good to go. You do the same thing on the other side if you want to, but you don't need to. On the output side of the transistor, in the collector circuit, you want to maximize the power supply through the power transfer through the amplifier, which means that the impedance presented to the transistor on the output side in the collector circuit should be the same value as the input or the output collector output resistance, which you can calculate or you can measure it basically. Some people use 200 ohms for that. Other people actually calculate it. Charlie Morris shows how to do that. Basically what you do is you take your transistor circuit, your transistor, and you measure the output voltage open circuit, then you put a resistor into ground and you get the resistor value that takes it to half the value, and that means that the resistance is then you read the resistance off the pot, and that tells you what the internal resistance is. In this case it was 340 amps supposedly. And given that you're dealing with a 50 ohm output on the transistor circuit, that means that the turns ratio is 2.6 to 1. And a ferrite transformer with 16 turns on one side and 6 on the other gives you 2.6 to 1, so you're good to go. And you calculate the inductances and do the same kind of check to make sure that the reactance is on the output side, in this case the 50 ohm side, is at least 5 times, which it was. So the other values in the circuit are the resistor that's in series with the power supply. It's there to provide isolation. Doesn't much matter what you pick. You can actually do without it, I suppose, but most circuits seem to have 10 to 100 ohms. I chose to put 100 ohms in. And the 2 capacitors to ground on the collector side are chosen to make sure that the AC voltage on the collector is 0, and also to eliminate AC wise and to eliminate power supply noise. And Peter's circuit had a resistor between the collector and the power supply, and the output voltage was developed across that resistor. In this circuit, the output transformer is the load for the circuit. In RF circuits, you do that. You either do it with a straight transformer, 6 turns to 12 turns or whatever, or you do it with, you can also do it with the tri-filler wound, 10 turns on each winding, if that's what you're looking for, a 4 to 1 turns or 2 to 1 turns ratio. You can do either. Anyway, they come out, these capacitors, one comes out, typically people seem to use 100 microfarads and 100.1 microfarads, gives you a bit of a range. And like I say, the feedback resistor and capacitor I'm not dealing with here because didn't put it in. So in the end, this is what you get. On the left-hand side here's the transformer, the input transformer with 6 turns on the input, 12 on the output, with the different 2 reactances, which you can calculate. There's the input capacitor. Here's the two resistors, the 3.9K and the 22. Up on the top here are the two capacitors with the two values. Here's the 100 ohm resistor back to the power supply over here. Another transformer on the output, and the voltage, output voltage gets developed across here. And a capacitor, a coupling capacitor, likewise 100 nanofarads. And the turns ratio is calculated accordingly. Now down the bottom here, you can't see, there's two resistors in parallel, 270 ohms each, to give you 135, which is close enough to 130, which is what the design called for. There's the emitter capacitor, 100 nanofarad emitter capacitor right here. And on the output, you've got two resistors in parallel to get 50 ohms. They seem to do that people seem to do that rather than putting a 50 ohm resistor or 150 ohm or 51 or whatever. So that's what the circuit looks like, having gone through all these calculations. And you calculate the gain by, it's calculated by taking the collector load impedance and dividing it by the total AC emitter impedance. And when you just go back to the circuit here, the emitter resistance is the internal resistance inside the transistor, the small RE, plus whatever you've got between here and ground, between the emitter terminal and ground. And because this is fully bypassed by this capacitor, that means that the resistance in the gain equation is just the internal transistor resistance. If you put a resistor in parallel in series with this capacitor, you can adjust the gain by fiddling with the value of that resistor. And basically you take, so the calculation is take the output impedance up here. Yeah, let me go back here. You take the collector load impedance, which is that 340 ohms we talked about before, divided by the total emitter resistance, which in this case is just the small RE of 2.6. So having done that, you calculate the magnitude of the gain, which is the ratio. And in this case, it would be 340, which is what we assumed the collector resistance was, divided by 2.6, which is 130.7. And that means 42 dB of gain, supposedly. And this is where you depart from, where the theory departs from reality, because it actually doesn't work that way. It comes close. So this is an LT spice plot of the gain versus frequency, starting at 3.5 megahertz and going up to, in this case, it's actually part of a plot, goes up to 30, but you can see the dark blue curve is the gain. And here at 7 megahertz, which is what I chose to run my simulation at, my actual breadboard circuit at, the gain is 28 dB, not the 43. But hey, so this is the LT Spice AC analysis. This is the time domain analysis, and you can see the input circuit, the input and voltage here on the signal generator side of the transformer, and its peak to peak is 25 millivolts here, and the output is same thing for the output circuit, and its value is 1614 millivolts, 1.614 volts, which means that the magnitude of the gain is 64.6, which means the gain in dB is 36. Which, if I go back here, 8 is not so far off 36, so it sort of works. And another thing, one of the problems I had actually doing this on a breadboard is how do you get such a low voltage out of a signal generator? And I hadn't figured that out yet. You do it with an attenuator, but it's not very satisfactory because you get, when you do this with a sine wave generator like the Field Tech sine wave generator, you get really distorted voltages at these low figures, but it doesn't matter on the output. It looks pretty good. I'll show you in a minute. So yeah, this is my breadboard stuff. nice looking sine wave on the output, but this is just a mess here. It's almost a sawtooth thing. And that's got to do with the ability to get a good clean signal at such low voltages. And I actually use 0.7 of a volt out of the function generator and put in attenuation to get around, try to get close to the 31 millivolts, but it's not very satisfactory. WA2EW has a way of doing this with attenuators and whatnot. I'm going to try that sometime. But anyway, when you calculate the gain here, it's 37 dB, which is pretty close to what the simulation says. So, yeah, this is the last slide. My comments that LT Spice is roughly right, seems to work more or less. Actual results can be better, whatever better is, or may not be than LT Spice. So it's really, as I said, it's really difficult to get seems to be really difficult to get a low voltage input signal, even when you're using an attenuator on the source side. And I think the square wave response would be similar to the sine wave response, but I wasn't able to check it because I can't figure out how to use a signal generator, which I have. And it's interesting to see that this is the second time I've done this with just breadboarding these things, and it works. You don't have to go to the trouble of doing a PC-based design with all that etching. You just plug stuff into the board, and it works. The fact that the board has capacitance all over the place doesn't seem to matter so much at the frequencies I'm using, 7 megahertz or whatever. At VHF, that wouldn't be the case because there's all kinds of capacitances come into play. So yeah, so that's where I am. I've looked around. There's stuff out there telling you how to calculate the bandwidth of the amplifier, and basically it depends on what the capacitances are in the circuits, and you can figure that out as well. I haven't done that yet. Anyway, so that's really all there is. So I'm going to stop here and come back, I hope. Where'd it go? Oh, I got to get out of here, don't I? Where is it? Yeah, so I'm back. Questions, comments, Brooks? Is Dave still here somewhere? Oh.
Yep.
Yeah, by the way, I used my new oscilloscope to do this stuff, or whatever that's worth to you. I love it.
Cool. I've got a question too.
Okay.
Okay. You said you saw a discrepancy between your measured dB and the calculation?
Yeah, it's not as good as it would be.
What's the difference? Did you say it was 2?
I don't think it's 2. It's like 40 dB versus 30 or something. I'd have to go back and look.
Okay, because one of the things you have to be aware of is power dB and voltage dB are different.
Oh yes, I know. Yeah.
Yeah, because it's a factor of 2, because it's a V squared.
Yeah, you got to use the right formula, which is 20. The voltage gain is 20 times the log, and the power gain is 10.
Right, and that 20 comes from the fact that it's V squared.
That's right.
It's a V squared term. So you take the 2 out of the log. But the power, the other thing about power dB and voltage dB is that the impedances must be the same.
Yeah.
So if you measure the input voltage, okay,
yeah,
and you look at the voltage, because that voltage is going into a different impedance versus the output, which is a different impedance. So your power is going to be different on either side.
Yeah.
So that may account for the discrepancy.
Yeah. Well, this is voltage gain I'm calculating here. It's not power gain, but yeah, I have to use the right resistances. That's right.
Yeah, because it's a V squared over R, and R is going to be different on either side of the amp, right? So that I don't know. I'm just throwing that out. That could be part of the discrepancy.
Well, let's see. The gain, the calculated gain was 43 dB. Voltage gain was 43 dB here, and when I actually went look at, and the LT, so that's the calculated gain. The LT spice gain was only 29. I'm not sure why that is, but I'll have another look at that anyway. Yeah, so that's where I am.
I think Peter's got a question.
Okay, Peter, go ahead.
Yeah, thanks, Michael, for this. I can see there's so much information in here. It's almost like we need to develop a worksheet, a step-by-step worksheet to work through something like that. It's good. Characteristic curves. It's been a long time since I've actually looked for characteristic curves, and I certainly, when I think back in my electronic courses I took I don't even want to say when, back in the 70s, I can remember looking at these characteristic curves, and I can remember that moment when the light bulb went off and says, I understand this stuff. Of course, that was back then. I'm not so sure today. But the comment I have is on the measurement of the impedance, the output impedance of the circuit, where you're using, you measure the open voltage first, and then you put a resistance in there, and then you measure that voltage. Then you do all the math, and you come up with the impedance. I can't remember exactly what project it was. Maybe it was a D612 project. I can't remember. But I started to get curious about the results I was getting, and I contacted Al, W2EAW, about doing this, because he had a video on it, and it worked really well. Anyways, I emailed him, and I asked him about it, and he said the method works great at everything except RF voltages, or at RF frequencies. So he did kind of say maybe one day he might get around to doing something about it, like a video on it, but I haven't seen one yet. So but it was far enough back, I can't quite remember what didn't work or what I was finding was wrong. So I was a little bit curious about that one.
Well, Charlie,
sorry?
Yeah, what Charlie Morris talks about is basically putting the transistor, just basically connecting it to a choke on the output to the DC supply, and measuring the open circuit voltage when just like that, with no load on it. And then you put a pot in there, and you adjust the value of the pot until you get half the voltage you started with, half the open circuit voltage. And that tells you. And then you measure that resistance value, because the voltage is half. The internal resistance, the Thevenin internal resistance behind the collector has got to be the same as that resistor value. And
until Al said, except at RF, but
except that, well, that's interesting. Charlie did it at RF.
I know, that's what, when you said that, I thought, well, geez, I remember Al telling me. Didn't work so well at RF. But anyway, maybe it's another experiment sometime down the road on the bench to mess around with that and just see what's going on.
I actually did that. I actually tried it, and that's where the 340 came from, I think.
Okay.
Yeah. Anyway, it can be done.
Okay.
Charlie Morris says, well, most people use 200, but it's not necessarily.
Yeah. Oh, I like Dave's little notes here, signs. One more comment.
There's all kinds of other stuff going on here, too.
I'll turn it over, but one more comment. I've noticed you're right, when you're trying to get your signal generator down to those voltages and you're putting the attenuators in there, but then when you're using such a low voltage that your probes are probably picking up noise left, right, and center. So you may have a clean signal going in there, but your scope will never show it.
Yeah. I don't know.
I don't think I would sweat it. I would say, have your output of your signal generator at a high enough value that you know for sure what the voltage level is, and then do the calculations down with the attenuators and make the assumption that your attenuators are accurate, and therefore you know what your input is, and don't worry about what the quality of the signal is like. Well, anyway, that's my 2 cents worth there.
That's what Al does. There's a video he has where he does something like that. Basically, what he does is he takes his signal generator and he cranks up the voltage until he can read it on his scope. I think that's what he does. And then he calculates what's on the output side of the attenuator, assuming the attenuator is accurate, and that gets him the input voltage to his amplifier. I actually want to try that, but I haven't done that yet. And I don't know, I have I have some of the 50 ohm loads for the scope inputs to make the scope look like 50 ohms, but I'm not really sure how to use those just yet. So I've got a couple of them, but I haven't used them.
I think your scope has a 50 ohm selection on it. That 200 megahertz scope has that.
No, this one doesn't. The 1202X does, not the 1202XE. One of them does, one of them doesn't. This one does not. This one does not.
Okay. Dave lied to me then.
It depends which one Dave got.
All right. I thought he had the same one as you. All right. Thanks, Michael.
Okay.
I think Dave had his hand up.
Yep, Peter, what you're talking about, he was talking about reactive loads for complex loads. Like that method of using a resistor works great if it's a purely non-complex, it's a purely real load. The minute you have a capacitive or an inductive load, I don't think it works very well. I think that's what I remember that's what he was saying in his email.
Mm-hmm.
Oh, okay. Could be. I'll have to refer back to it.
Would you mind sending me that email, Peter, if you still got it?
I'm assuming, because I hardly delete anything, and I'm sure I wouldn't delete his, but because of the information that's in it. But yeah, I'll take a look for it, and I will.
I guess the theory is on the output of the amplifier is the next stage is another amplifier perhaps, and it's got, the theory is it's got there's no inductance in that because it's basically transforming the input impedance, which is presumed to be resistive, back to 50 ohms to match the previous circuit. So you're like Dave says, you're assuming it's all resistance, but it isn't, because there's capacitances all over the place, and yeah.
But I think bottom line, Michael, it's probably good enough.
Oh yeah, it seems to work. I was just trying to just see what I could do with this stuff, and you're not trying to design a Ferrari here. So as long as it works. And the other thing, in the LBS project, all those circuits, the different circuits, all presumably are assumed to have 50 ohm input and output. And I think there was some indication that was actually the case on most of them. But who knows?
Yeah.
Okay, I got a couple of things on your input and output transformers. As long as those transformers don't form a tuned circuit, which happens quite often, you can't use the FT3743 because it will not work with the tuned circuit correctly.
Okay.
So you would have to go to, like the regular iron Potter ones,
Mm-hmm.
the T50s or T37, whatever size you need. But soon as you put a capacitor in there that makes it into a tuned circuit, you can't use those ferrites anymore.
Mm-hmm.
And for your input circuit, I think you get what, 12
to
6
6.
12.
12 turns to 6, yeah.
Just wind a 10-turn trifilar. It goes from 50 to 200.
Yeah, that would have worked too. Yeah, that's right.
Yeah. It'd be a lot easier because if you did 6 and 12, you would end up winding 12 and then a 6 on top of that.
That's
and
right.
then you turn around and think, well, maybe I have to take a couple of turns off of the 12 to get it to work correctly.
You can't get them. You can't get out.
Yeah.
That's right. But I did check the reactances or the inductances. They were pretty well spot on, close enough to where they're supposed to be. Yeah.
Now, I don't know if you remember my presentation on how to calculate the toroid or the windings. Wes Hayward gave me a lesson on how to do this, and his minimum is 10 times, not 5 times. Yeah.
Oh, that's interesting. Charlie Morris uses 10 times.
Yeah.
I don't know where that comes from. There must be a somewhere in some dark place. There must be an explanation of that, but I haven't found it. I haven't looked for it. To be truthful, I haven't looked for it.
Somewhere up in the cloud.
Yeah.
Yeah. Some people use 5. Some people use 8. Some people use 10. I just went with Wes's number, and I used 10 times minimum. but it really doesn't make a difference. I think as long as it's higher than 5 times, you'll be perfectly safe.
Yeah, you know, when you're building one of these amplifiers, it doesn't seem to matter all that much what assumptions you make. You end up with what you want, and you can control the gain by fiddling around in the emitter resistance stuff, and you know.
Yeah.
So yeah.
Okay, Hassan had his hand up.
Yeah. Can you hear me?
Yep.
Okay, so Michael, about your DC biasing slide, I was just curious. You started by assuming a value of beta and then kind of went and calculated VE and RE and all that stuff.
Yep.
Could you have done it the reverse way? You fix VB, you assume that VE is like 0.7 below that, and then
Yep.
you calculate IE from your resistor, and then IC is about the same as IE. And if you do it that way, then you don't have to assume anything for beta, and you may end up with the same results at the end of it, but
Sure. So you basically you pick the base voltage to
yes.
be 2 volts or 2.5 volts or something, and you go from there. Yeah, you could do that.
Yeah, I think that's usually the proper way to do common emitter design. So you have to make sure your base resistors are, I think the smaller the better, because then the more current means they're more stable. It's stiffer.
Well, that's why the 10 times. Yeah, you want to make sure the current through those bias resistors is at least 10 times the base current.
Yes, that's right. It means it's a stiff current source, or a stiff voltage divider. So as the base current changes, it won't swing the bias point.
That's right. And as the transistor warms up, it won't temperature changes. It won't affect it either.
Yeah.
Okay, anybody else for questions for Michael? No, I don't see
I just got
anything.
one quick one.
Okay, go.
Michael, way back in one of your earlier slides, when you're showing the characteristic curve.
Yep.
What was the number values on the right-hand side of that paper? I think it was
What
like
are
10.
they? They're the base resistor. They're the base current in microamps.
Okay, thank you.
Going from, I think it's 5 at the bottom up to 50 or something, or higher. Yeah.
Okay, thank you.
Anybody else? Questions, comments? Okay, I guess not. So let's Dave wants to talk about his half-built shack. Go ahead, Dave.
Actually, I'm not talking about my shack. I said that in a couple of weeks I was going to put a presentation together. What Pete and I talked about was having a new segment on the this forum, either on the, what's it called, Peter, the AF Mixer, the off Wednesdays, or the main meetings. Is to have a segment called, show us your shack, and basically, give us a tour of what your bench looks like. What have you got? Show us projects, show us the type of equipment you have. I notice everyone's looking around their shack. They're getting all nervous. That's kind of hilarious. But no,
Everybody's got to be cleaning up their shacks.
yeah, yeah. I thought I would start. I'll do the first one because I built my shack from scratch. It's now, you can kind of see in the background there. You can see the wires coming down from I made a cable raceway, and I'm just pulling cables to go to my antennas. And I've got my shack basically. It's set up. There's a ladder there in the background still, but I'm still, setting things up, but it's 80-90% there. So we just thought that would be an interesting segment that, anyone could participate in, and we all take a turn and we just give us a tour of what the shack's like. So I'll have something ready at our next presentation. I've already got pictures of the build along the way, and I'm happy to share that with you guys.
Okie doke. Alrighty. I'll show video of mine, opening the door and throwing a grenade in and closing the door. That'll be my presentation. Anyways, any other comments regarding the new segment?
Yeah, I got one.
Yes, sir.
Yeah, no, I think it's a good idea. We did something similar here in Kingston, and it went over really, really well. And so I'd be looking forward to seeing what this group is got going in their shacks.
Hey, so you got your camera at another angle, Peter?
Yeah, I'm using my laptop tonight. I usually
Oh.
use my other computer, but the screen started to give double images. And no, it wasn't because I was drinking today.
Okay. Next on the agenda is Kevin wants to introduce a new segment. Take it away, Kevin.
Hang on, turn the mic on. All right. I wasn't. Yeah, it was just sort of a inspired idea because I keep getting all these junk emails from DigiKey and various vendors. But oh, look at this chip. Look at this. We can sell you this. And some of the chips are kind of neat, and some of the stuff is kind of relevant to what we do. Others is, like who needs a 24 gigahertz radar chip? I don't know. I guess maybe Tesla does, but not something we could use much of. But apparently they're out there and they're not that expensive. So I thought, well, what if we had just a prodding where we would, show each other, well, I came across this chip and here's something it could be used for, or maybe we could use this as part of a buildathon, or it would solve a problem that maybe somebody's been looking to solve. So I thought it might be an idea to just ask during the presentations if anybody's run across something, or if they want to send the information to me, I can share it with everybody. So anyway, I just put together a little presentation here, just to talk about what I thought this would entail. Nothing fancy, but just why I'm doing it and what maybe can come out of it. So anyway, the idea is that, okay, it's a way to bring attention to, products. Sorry, can everybody see the screen? Yes?
Yeah.
Okay, all right. Way to bring attention to technology products that may have an application in our projects or homebrew or whatever. And it doesn't necessarily have to be a chip, but, just new technology, or even just new to you technology, right? So if you find something that looks interesting, and just to make it more, or less restrictive, and even, maybe a talking point, doesn't, just because the chip is $150, yeah, maybe it's still interesting. Doesn't mean we have to use it, but it's still interesting to talk about. I don't know. It's just, we keep looking for content, for these meetings to keep them interesting. And sometimes there's some pretty cool technology out there, and sometimes it's interesting just to bring it up and show what's going on. So, it's, if you have a link to the data sheet, what is it you find interesting about the chip? Maybe some possible uses, and if you know the cost, because it's always good to know, what are we in for, right? I mean, how much is it going to hurt if we have to use it in a project? I mean, I was looking at some chips earlier. It was like, one of the things that SpaceX is doing with their Ether, or the Starlink, right? All the ground stations are all phased array satellite comm stations, right? So they have to have, and they're not that expensive. So they have to have some pretty fancy integrated electronics to do the phased array antennas on there, right? Because it's not rotating. But they do, they always know where the satellites are, so they can follow the satellites with a phased array antenna, which, it sounds kind of cool. So anyway, that was just another thing that I ran across. And if you I prefer that other people present them to, if you find something, please present it to the group, because that gets more people involved in the meetings. But if you don't want to, you send me the information and I'll talk it up. A couple of chips that I ran across recently. I mean, these are new to me. They may not be new to anybody else, but here was one that I came across. It's a multiplexer chip. So you can use it for switching analog and digital signals up to 5 volts. The bandwidth is 500 megahertz, and you can switch one of 8 or 2 groups of 4 based on just some logic level inputs. So it basically takes the place of relays. Now the resistance of the channels is higher than a relay contact, but also the impedance is probably a lot more controlled, and they don't wear out, and they don't corrode, and they don't do things like that. So, and the isolation and crosstalk is pretty impressive. I mean, it's minus 90 dB between channels. So anyway, I thought that was a pretty cool chip, and it's only 76 cents. So you could use it for audio, you could use it for video. They use it for switching like closed circuit TV cameras. So for HF stuff, it's a walk in the park, apparently. To indulge me.
Recording is on.
There's I know we always talk about mixers, and I know what is it, the 602 and 612 mixers. I found I ran across this one. It's from Analog Devices, a high signal level active mixer, good from 1 kilohertz to 3 gigahertz. So it doesn't matter what we want to do, it'll do it. It's got conversion gain instead of conversion loss, which I think the 602 doesn't have any conversion gain. You can do resistive impedance matching, so you don't need transformers. You can run it single-ended differential. It just got a bunch of neat features that make it more useful, but it's also $13 instead of whatever 602 is. I don't know, 50 cents, $1, whatever. So anyway, that was another one that I ran across, and I'm sure there's hundreds of them out there. And anyway, there we go. Okay. So anyway, that's the kind of thing I was looking at. So I think, Dave, you wanted to speak. Go ahead.
Yeah, Kevin, that's awesome. I think this is, I love this segment. This is going to be good. I especially like that chip, the first one you did, the Mux, because I played around with some of these chips, and I've never gotten close to the isolation that they claim, and I suspect it's probably because of just crappy layout. My traces are too close, or I'm feeding in a signal too hot, and I'm getting stuff bleeding through. But I've never had any success with any of these chips. Now, is that chip, does it come in a really small footprint, or can you get in a big, massive?
No, I don't. I don't think any chip comes in a big footprint these days. But it's funny you mentioned that. In the data sheet for that chip, they specifically give you guidelines on laying out circuit board traces. They actually go into that just for that chip. A lot of chips don't, but that one they do. And I suspect what you're onto something with that, and that is you have to be very careful with how you lay out your circuit boards. Even things like they don't want 90-degree bends in corners. They want nice curved corners because it changes the impedance. Right?
Yeah,
because the impedance is a trace width, so your trace width changes at the corner. Whereas if you have a radius circled, the trace width is constant.
I've even seen that for power rails, power supply traces too, where they say they don't use 90-degree bends, except I guess for if it's low frequency stuff.
Yeah,
right?
really low frequency. But this thing, like they said, the bandwidth is 500 megahertz at 5 volts. So, I mean, that's pretty much anything we want to do.
Yeah, that's incredible.
At least in my world. So,
yeah.
If you want to switch antennas or, almost anything, it looks pretty useful. For 76 cents, it's like, how can you go wrong?
Because I hate relays.
Yeah, me too. And actually, when I saw that, I was thinking of like our, the PARC, the project, this thing, Little Pup. That's it. I was trying to think of the name. We have a little switch in the side here, right? And I always thought it would be so much better, I think, to have a low loss and non-corroding type of switch in there. And that's always been something I've been meaning to do to this thing. But anyway, there are tons of these things out there. I mean, it's just mind-boggling when you start looking around. Even DigiKey sends me a hard copy, little brochure, I don't know, once a month or something. I don't know why, but anyway, they send it to me, and it's like it's got all these neat chips in there. And so anyway, this was just a way of trying to get more people aware of it, or if you're interested, share the knowledge, and maybe somebody will have a brainstorm and come up with some really cool application. So anyway, that was it. That's my 10 minutes.
Peter, you had a question?
Not so much a question as I got just a comment. Dave actually spurred me on to making this kind of comment. I'll do a presentation on this down the road somewhere, but I think you'd be surprised at how small you can go. Last week, I took an interest in, just quickly here, digital pots, digital capacitors. And of course, as Kevin pointed out, they're pretty cheap. They were like 77 cents a piece. And so I bought a couple each of the various types. The problem being is, one was the a 6 DFN package. That was the capacitor, the digital capacitor, and the other one, the pot, was the SC70-6 package. So breakout boards aren't cheap anymore, at least the ones that I wanted. So I was able to do something there, and like I say, I'll put that in the presentation. But I decided to start etching my own, see if I could etch that small. And just quickly here, I was successful with the SC70-6, and not so successful with the DFN chip. That I have to think of a plan B or a plan C on that particular chip. I haven't given up, but I know what doesn't work. Anyway, so don't be afraid of small packages, and they're cheap anyway. So, okay, that's all I got.
Okay, any more comments? Anybody? No? Okay. Yeah, I was back to when we were trying to use that LTC, I think it was the 6900 oscillator. Little tiny chip, could barely see the thing. I was hoping to be able to use it for a VFO for the DCR, but as Frank and I found out, it doesn't work so well. It drifts too much when you get too close. If you don't load it properly, it doesn't work properly. But that would have been really cool. And I think they were less than $1 a shot. So, yeah, we got to look for stuff like that. Okay. Nothing else is slated right now. Now, back in our AF mixer at the beginning of the month, I was speaking about Diz of Kits and Parts. He is in the process of converting all his kits to SMD. He's introducing the new kits. He's retired probably about 80% or more of his existing kits because he's switching over. One of the latest ones he's come out with is a direct conversion receiver. Much like our design, he's got a couple more features in it, like AGC. He's got side tone input. And I think there's another one I can't remember. Anyways, he was looking for guinea pigs to try it out. I ordered 2 kits, one for a DDS input and a DDS for a DDS VFO and a wideband input, and a second one with a 80 meter Cura P crystal that's adjustable a few kilohertz. Well, I've built the one for the DDS, and it works very well. The only thing I have left to do on it is I have to build a 200 to 50 ohm transformer because the input is 200 ohms and our SIGGEN is 50. So I'll probably have that done on the weekend. I can do a little video recording. He's what he intends to do is to build modules that you can link together to form a radio. So the DCR is actually the first stage, and he's in the process of a variable bandwidth crystal filter. You can adjust your bandwidths for CW and sideband, and he is prototyping the boards right now, and I'm assuming he's going to be wanting guinea pigs to try that one out. So I'll probably get my hands on that. And he's going to continue so that you can buy different modules if you want and build your own, or just build all the modules and just make a super het receiver. The exact cost is not known yet. The guinea pigs paid $10 US for a kit, but once it goes into full production, there'll probably be a minimum of $20 US plus shipping. That's very comparable to our DCR that we're planning to build someday, which I still got to work out. And I don't know. Do we continue with our DCR, or do we look at Diz's kit? Any comments? No comment. Okay.
Yeah, I had my hand up.
Oh, I didn't. Sorry, it flashed. Oh, okay. There they go. Okay. So Peter first, and then Dave.
Well, first, the one comment I did have was what was the shipping of that kit up? How much was the shipping on that, Ken?
0 for me because he screwed up.
How much would it have been?
13 US.
That's
okay, that's for 2 kits.
Yeah.
Now I don't know how many kits he can get into a package. They're very small. I think it's a 3x2 board, and all the parts are SMD. So how many of those kits can you put into a small box?
Yeah. Okay, and the other one is, yes, continue on, especially until the December exec meeting.
Yeah. Go ahead, Dave.
I'm all for using our own designs. I think instead of using someone else's, we design this ourselves and we put the labor into it. And if it costs a little bit more, well, so be it. It's our kit. And I think there's a little bit of pride in terms of doing that. Anyone could go buy a kit and build it, but I think it's really cool that in our club, we take kits, or we take existing designs and we tweak it and we put it out as a kit. I think that's one of our strongest features that we have as a group.
I absolutely agree. I wasn't asking if we should switch over. I just wanted some opinions, what other people thought. But yeah, his design and our design is pretty much the same. The only addition he's got is the AGC, audio derived AGC, and he has a side tone input, and he's got mute. That's what it is. But other than that, they're pretty much they use the same chips. Everything's the same.
Is it? Are these designs on his kits and parts site, or?
Yeah. The DCR is there. I don't know when it's going public, sale to the public. He may still have it temporarily unavailable.
So Hassan, look at Kits and Parts website. I think if you just Google Kits and Parts, you'll get the website.
Yeah, just go to Kits and Parts. He'll have a menu on the left side. Go down to RF toolkits.
All right, try that.
Yeah, so yeah, we can go ahead. Now, another thing is Peter and I were discussing, it was actually Peter's thoughts to approach the executive to try and fund some of this stuff, some of these the cost of these kits. Peter wrote up a little couple paragraphs. I submitted it to Al, who happens to be on the executive, and he has sent it to the executive. And that, unfortunately, I wasn't able to make it to the last general meeting. Peter was. The next executive meeting, I think, is December 8th. So I'll make sure that I'm there. We are asking for if they could fund $20 per kit to a maximum of $20. So if the kit actually costs us $50, then the club would flip $20 per kit. So that'll come to you as $30. But we'd have to wait and see what their decision is. I can't see why not. Go ahead, Peter.
I was just going to make a comment about us designing our own kits and going ahead. That the preferable way of doing it, and even if it is a little more pricier than what else is out there. Dave can certainly, and Eric can attest to these, the comments that we got at Club Night at 4 Days in May on our projects that we've designed in-house and presented down there is certainly is enough encouragement to keep going down that path, even if it is more expensive.
No, absolutely, absolutely. One thing I do stress that we should change, get rid of the through-hole components. Let's go SMD everything. Because the cost of SMD parts is a small fraction of through-hole parts. But anyways, I'm going to be getting hold of Kelly for a couple of changes on the board. Hopefully he'll be able to mill a board so we can try it out. And if it's a go, then I'll try and get him to give an estimate on the cost of a PCB. And I can come up with a final price. So far, we are looking somewhere around the $35 to $40 mark, and that's not including the PCB. So that's where you are right now. Coolidge? Okay, so anything else to add to the meeting from anybody?
Hey, Ken, Frank's got his hand up.
Oh,
He's blinking in and off, and I think Kevin had his hand up as well.
okay. I'm not even getting those messages. Okay, I see his hand. Okay, go ahead, Frank.
Yeah, and I wanted to comment on buying a kit versus building and designing our own. One, I completely agree with the comments and the reason for them and why we should continue in that way. However, there is one thing that I would like to mention is that over the course of the years, we have done both. We have designed our own and we have used kits from other people. And without a doubt, the percentage of problems we have encountered during the buildathons has been much higher on the kits that we have purchased from other sources. Everything from flat out, it didn't work on the day of the buildathon, to missing parts, and to, in one case, a complete design change had to be made before the buildathon. So keep going, fellas. I'm going to have to operate from a remote standpoint, but you're doing a great job, and good luck with it.
Yeah, we should be okay. It's just it's taking a little longer. One problem is getting hold of Kelly. You know how long that took to get hold of him, almost 2 weeks. But anyways, I'm going to be contacting him with a couple of changes. They're not major changes. We need to move things around and do something about the bandpass filter plugin. But other than that, we should be ready to go. I will once Kelly can work out a very good ballpark cost of the PCB then, and I can work out the final cost and also see what the executive says about flipping $20 per kit. More to come. Any more business, people? Oh, Hassan had his hand up. I think Dave had his hand up.
Yeah, so I bought this kit. It's funny Frank mentioned that because I bought this RF amplifier kit off eBay or Amazon or something, and it's notorious for having no documentation and everything. So a lot of people have tried to, document it and just describe how to actually build this thing, because instructions make no sense. It's based on something in EMRFD, some classic design. But it's all got surface mount parts, and it's a 45-watt HF linear amplifier. So I was wondering, what's the best way to actually do surface mount? Should I just get a really thin soldering iron, or should I use solder paste and a hot air reflow? What do you call those things?
Reflow oven?
Something like that, yeah.
Yeah. Well, I just built Diz's DCR, which is all SMD, and I just used a temperature-controlled solder iron. It took a little longer, but I got through it. And it's not that difficult. Once you've done a couple kits, a kit or two, you get used to it. I think, Frank, you got the reflow oven?
Pardon, the which?
The reflow oven.
The reflow oven is with Simon.
Oh, okay.
And it's available. It's in his office. In that regard, any boards that we designed ourselves, we are also able to design a template to use the solder paste on it. And a lot of people that never tried surface mount before were very successful in using that method, while other ones shied away from that method and wanted to put the parts in individually. But in either case, it worked out better if we designed our own surface mount board.
Yeah, okay, absolutely. What was I going to say? I think all the PCB manufacturing houses do provide a stainless steel paste stencil. I think the one SMD one we did, Kelly did get one with the PCBs. So if you actually order an SMD board, you'll get a template for it automatically.
Good.
2 questions. Can I 3D print one? And can the 3D print actually drop solder paste onto a board? Because that would be the ideal solution.
Yeah, you could, but the purpose of the stencil is just place it over your PCB, put some paste down onto the board, and you swipe it across the board, and it leaves the paste on the pads. And then you place your parts on the pads, and you stick it into the reflow oven. Or you can use a hot air gun too.
Okay, thank you.
Who else had their hand up? I think Dave.
Yeah, Hassan, if you look at, here's the D612 board I built, and if you look, it's, oops, can you guys see that?
Yeah, sort of.
Yeah, I clicked the, I clicked the button here. So you could kind of see a lot of it is 1206 parts. And with 1206 parts, it's easy to use a soldering iron. Now I made the board fairly large so that I can get in to tight places so I can solder those parts. But yeah, like 1206 resistors and things like that are fairly easy to work with. If you're going to get down to like the tiny little, SOT packages and the QFNs, good luck. And then the last thing I wanted to say before we close off was I have this belongs to the group. Okay, it's a signal generator, and it goes up to, what does this go up to? 5 megs? I think it goes up. Peter, what does this go up to again? Do you know? Can you remember?
I can't remember. Not high. You might be right at 5 megs. It's not much higher than that, I don't think. Maybe 10, but I don't think so.
Yeah, it's like it's not very high frequency, but I've got it here. I have used it rarely, and I think it's time to maybe pass the torch on to someone who can use this. So if anyone needs this, next time I'm in town, I can drop it off for them. You're gonna have to sterilize it.
Yeah, I'll take care of it. I'll see you at the campsite next summer, anyways.
Yeah, hopefully I don't have to hang on to it till next summer.
Who else? There was Peter and Mike. Okay, go ahead, Peter.
Yeah, just a comment about the stencils. It's been a while now since we've done the stencil project where we used the stencils on the oven. But back then, you had two options. One was the steel one, and the other one was plastic, a stencil, and the other one was plastic. We went for the plastic because it was really a one-off project, and the steel one was quite a bit more expensive. But we had to pay for that stencil, if I recall correctly. So we went for the plastic one. But maybe things have changed. But I would double check that thought, though, getting a free steel stencil, though.
Yeah, I think Diz was talking about it on the Kits and Parts IO group. He said that they had 3 choices. One was the stainless steel, which he went for. They also had I think a plastic version, and they had another version that could only be used about 6 times. I think it wasn't paper, but it was something else. So I think they've stepped up what they can provide depending what you're willing to pay. Who else was there? Who else had their hand up? Too many hands going by.
I did, Michael.
Okay, go ahead, Michael. Sorry.
I haven't done. I've only done one PCB board. That was with Ed Spingola. We did a interface project for our club station, but I haven't gone there because I'm concerned about the chemicals and what to do with them afterwards. How do you get rid of them? Getting stains all over the place, those kinds of things. There's this idea using muriatic acid, which seems maybe somewhat dangerous, and then there's the other stuff. But I know we're going to be talking about KiCad and how to one of the presentations about KiCad and how to do, I presume, how to use KiCad to do printed circuit boards. But I'd like to know, maybe we could also, somebody could also talk about, well, how do you actually go about doing this stuff in a safe and clean way, if that's possible. Anyway, just a thought.
Okay. Who else had their hand up? It looked like you were going to say something there, Mr. Ian. You zoomed your camera in.
I want to say something.
I have a question.
Oh, your audio's really bad, Ian.
Yeah. Not very good on this thing. Much.
Can't make out a word you're saying. Go ahead, Peter.
I was just going to say to Michael's points, what he's talking about with the etching. What I do is, of course, I save the used etchant, and then I take it up to the hazardous disposal, and I have no problem. They have no problem accepting it and taking it. So that's not an issue of getting rid of the used chemicals in a safe manner. And as far as Stains, well, I etched in this shirt the other day. Sometimes it happens and sometimes it doesn't.
Wear an apron.
Hydrogen peroxide and muriatic acid works fantastic. It's, I tell you, it's so much faster. You don't have to heat it up. You don't have to agitate it. You just put it in, and it within 5-6 minutes, it's clean.
Yeah, so far I've just been using the ferric chloride.
Okay. Well, if somebody wants to demonstrate or talk in lengthy detail about how to etch boards, that'd be a great topic. I tried doing one with the ferric chloride and a pen, and it didn't work out very well. But mind you, I haven't done a circuit board since the mid '80s. Hands were flashing up, but they were going by too fast. So who else says something to say? There you go. Cool. So is that it, guys?
Jerry has his hand up.
What's that?
Yeah. So my question is to Dave. Like, I think you have a new shack, and Dave, are you there? Can you hear me?
Yes, sir. Yep.
Yeah.
I was on mute.
It's Jerry here. So I believe you have a new shack, and I think you have probably taken cables from your antennas to inside your home. I have talked on this earlier. I think to a couple of people already. So I think I talked to Frank on this also. So I am I actually moved into a house last year from an apartment. So I'm just trying to get some cables from outside of my home to the inside. And my shack is actually on the first floor, and I'm actually having some difficulties drilling a hole through the wall. Like, anybody has got any advice for me?
Is it brick?
It is brick, and I think there are like several materials inside the after the brick, right? Maybe there is kind of wood and insulation and all that. So I'm not sure what is the composition of the. I mean, like, in between the drywall and the brick. And what happened was I was drilling the hole up on a ladder. When I was drilling it, I think I went past the brick, and there afterwards it became very tough to drill in. And what happened is I started the impression of getting a smoky something coming out from the hole. So I immediately poured up some water and stopped there then and there. So. And I also looked at getting somebody to actually drill a bigger hole so that I can put maybe a smaller 3x4 inch pipe or something and get all the cables in and out, whatever I want. But yeah, unfortunately, I'm not able to get someone to do that for me. And I'm not sure like what is the best way to do it, because I'm not drilling from the inside of the house to outside. I'm doing it from outside to the inside, so that it will be little less messy, or anything that I don't know, maybe it's much more better. And I'm doing looking at the electrical code also, because I'm doing it about 12 to 15 inch, which will clear out all the electrical cables, and there is nothing in there. So
Jerry, my advice to you is be very, very, very careful. You're saying you don't think there's anything in there. I would cut a hole in the drywall, and I'd look what's inside there, because the last thing you want is to drill into some electrical wire or plumbing or something in that wall, which could really cause you serious problems. It's better if you break the drywall is easy to patch as long as you can color match the paint, right? I was kind of lucky in my house. I had my house drywalled, the basement drywalled, and if you look, you'll see I have a whole bunch of access panels, holes in the wall, in the ceiling. I have a raceway that I run my cables through. So I've got you can see the raceway there. Here's the cables here. You can see the cables here. coming down.
Yeah.
So I drilled a hole going from the outside of the house to the inside, but my basement's not finished where I drilled a hole so I could actually see the wall. I could see the cinder block. So it's just a matter of drilling through it. I knew that there was nothing between the bit and the inside and the outside. So you got to be very careful. You don't drill into something that's sensitive.
Yeah,
Okay.
go ahead, Peter.
Okay, Cherry. There's two ways you can go about it. First thing to do is if you're trying to hire somebody to do it, try and call an electrical contractor, and just sort of saying you want them to drill. You probably want to drill at least a minimum of a 2-inch hole through there, maybe even a larger one, and ask them that's what you'd like to have done. You want to get them to put a nipple in it and a weatherproof box on the outside, so it's a little quickie job for them. They may go for that. Otherwise, what I did here was I went up to the United Rentals and I rented a rotary drill with I think I put a 2-inch hole through the brick, and then I used a hole saw. Once I got into the wood header, then I drilled with a hole saw to come in. Now mine's in the basement. Sounds like you're going to be above the basement level, so I would say what Dave had suggested is open up the drywall where you are and then poke in there. You're on an outside wall, so you're not likely going to find a copper pipe there, but you may find a 110 line. So you want to make sure that's not in there. So be careful with that. And then once you do that, then you can come, like I say, you can use a rotary drill that you can rent. It's much quicker to do it that way. Using a regular drill with will take you forever. But see if the contractor will do it for you first. But try electrical contractor. Anyway, that's my 2 cents worth.
Okay. Thank you. Thank you.
Anybody else got anything to ask or comment on?
I'd just say that if Cherry, if you're bringing cable inside the house, just also pay attention to lightning, because apparently it'll actually travel through the cable into your house. So make sure you have like surge protection or whatever, lightning protection on the outside.
Right. I plan to do that because I was reading that book from ARRL on that grounding. So I'm planning to put a small earth outside, and I plan to actually ground the coaxial cables over there into the future when I do this. Yeah. Yeah. Thanks, Dave, for the advice as well. I was also using that same drill, that masonry bit, but I think after the brick I hit the wood. Maybe that's why it was not going in. Yeah.
Yeah, a masonry bit will not go through wood, especially a 2x4.
Yeah, because this is on the second floor, and I am actually standing on a ladder, and I'm actually to get to that level. I am not able to see very much, but I was holding the drill. So yeah, I think after a while it became very hard to drill. Perhaps that's the time when I hit that wooden piece or something wood in there. And I was so confident because there was already a satellite cable coming into the house, but it's a very thin line, so I cannot use anything useful out of it. Perhaps I can squeeze a RG58 in, that's all. So that's why I did not drill through the same hole. Instead, I wanted to put another one and see. Yeah, perhaps it's the best use case scenario to have a electrical contractor come in and do it much more safely. I don't. I mean, it's okay to spend some money on it, but I just wanted that, done as early as possible. So, in order to get some edge of stuff. Yeah.
Yeah. Okay.
Also start with a small hole. Start with a really small hole, get it through, and then I used a bigger bit, and then I drilled through that. Peter shaking his head.
Cannot hear you.
You're muted.
If you get the right size bit and you get you have to rent the rotary drill, and then that'll hammer it right through the brick in about 30 seconds, if that. That gets you through the brick, and they get you a nice smooth hole to the dimension that you want, and then you're done in one fell swoop. And then you do the same thing with a hole saw.
Yeah, I've got a hammer drill, so I used a hammer drill
Yeah.
to make it through. But I chose to do a small hole just to make sure I could get through. Then the bigger hole, it was a lot easier, I thought.
And then the best size of the hole would be 2 inch, based on your experiences, like 2 inch.
Depends on how many coaxes you're going to put through there. If you put about 4 coaxes there or 5 coaxes in a 2-inch hole, then you won't get one through with a PL259 on the end. You'll be soldering outside in the middle of February. How do I know? It's really hard to hey, try and solder a PL259 on outside in February.
I used a 1-inch hole because there's only one piece of coax going out, and I've got a switch. I've got a remote switch, so the cable goes in here, and I can put 4 antennas to this, and it's a remote switch. So this gets mounted to my outside wall, and the cable comes in under here, plugs in, and I got 4 outputs. I could connect 4 antennas. So I chose a small 1-inch hole because I only needed 1 cable going out.
There's one in every group.
Hey, Peter, the end that you have to put the connector on, push that through the wall from the outside so you can solder it in on the inside of the house.
Yeah, I wonder why that didn't work. Oh, I think it was because I was doing a repair. But yeah, I see your point.
Okay. Anybody else? Doesn't look like it. Okay, guys, it was a good night. Good discussion. And that's it for tonight.
Okay.
Thanks,
Thanks, guys.
Okay,
Thank you.
guys.
Night.
Have a good week.
Bye.
Bye.
See you later.
Bye.
Whatever happened to that Eric guy? Oh, there he is.
I'm here.
You're quiet.
Hiding in the background.
Quiet. Yeah.
Did you have a hard day at the office?
Hard day at the office. No. I just decided to be a lurker today. That's all. So.
Did you ever figure out why the recording goes off and on?
Yeah, not at all, unless somebody's hitting the stop button. But I think that problem has been licked, so maybe it's just a Jitsi bug. Who knows? So,
Like
anyway, not a big deal.
hit the record button here, but I don't think I can stop it. Can I?
I think anyone can press it. I don't know. Try it. We don't need this part recorded, so press stop recording.
No, that didn't do it.
No.
Oh, really?
Yeah, I think.
Oh, wait a minute. Yeah, but it also asked me to confirm too.
Okay. So
somebody has to really want to do it.
Yeah. Okay, so it's probably just a bug then. I thought somebody was just fucking around with the buttons, and but by this point,
knowing your relationship with another party that's not online at the moment.
Yeah. Nice guy.
Anyway,
I hope he puts some paste on that bit before he uses it on my visit. So.
Yeah. Oh, actually, the 2 right guys are still behind here. Peter Taylor was mentioned to me that the schedule that I've drawn up is finished this month. Well, next month. So I've gone ahead and I've done a schedule for next month. Are we all 3 of us still good to go with what we're doing?
Yeah, it's fine. Yeah, it's working. Yeah. So sure.
Okay, so I'll send it off to Peter, and I mean we're flexible. We can always change things up as time goes. If somebody can't make it, we can substitute in and out. But just to put something out there that people can see that there is, you know.
It's nice to see a few of these segments coming in as well, eh? Like the shack and the chips and all that. So
yeah.
That's what we need more of.
We need some of that stuff. You're right. Any ideas for next Monday, or not next Monday, but the first Monday?
Beginner's Corner.
Who?
Beginner's Corner.
Okay.
Where's Klaus? I actually haven't seen Klaus in a while.
You know, he really pissed me off there a couple of months ago. Because I was at the regular park meeting, the first one they did on a Jitsi session.
Yep.
And he went off on a tangent saying how we talk way above his head. He doesn't understand us and all this kind of stuff. And yet we were setting up some really basic stuff for him. And then we'd be sitting here talking about some basic stuff, and he's not even there.
Yeah. Or
presentation today.
Pardon? Oh, yeah, that would have really blown his mind.
Yeah. Or I always, when Klaus is in the meetings, I purposely ask him, do you have any questions? You know, do you understand? And he doesn't say anything.
No, but he really said a lot at that meeting. I wished you were there because, matter of fact, I wrote up a big email to send you guys, and then I got it off my chest, so I never sent it because, you know, you don't send things off, and it really pissed me off. But anyway, so, but I think we should still carry on with our back to basics routine too. So
yeah,
in spite of that.
Okay.
I guess we have to appeal to the whole demographic here, right? You know, the comment in the chat there was, hope this is being recorded to use as a future reference, right? So
you better edit out what I just said because you're still recording.
I know, yeah, that's right. Too late. This is being posted right to Klaus's Twitter feed.